end. So I don't know. I doubt you can see me. Can you hear me okay?
I can hear you.
Yeah, I can
Okay.
hear you.
I can hear you.
All right. I'm going to step out. I'm going to end the meeting real quick, but I'm going to rejoin it here. I want to see if I can get the video back up again. Okay. So hang on just a minute. There was an interesting news article for the few of you in the class who are interested in astronomy. There was a new article that came out today, as a matter of fact, when stars live out their life, and stars do die, and Some of them, blow up as supernovas. That's actually kind of rare. Most stars don't die in that fashion. Most stars like our sun, and our sun is going to be one of these, is going to eventually end up as what's called a white dwarf. And basically, it'll be the surviving remnant of the core of our sun. And because there's no more nuclear reaction being created in the middle of it, the core is going to get crunched down quite a bit. This white dwarf is probably going to be under normal circumstances, it might possibly be the size of the Earth, with the entire volume of the core squashed into the Earth. That's a white dwarf. Well, what was in the news today, they've discovered a white dwarf that is next to them. It's the single densest white dwarf they've ever found. Imagine the center of our sun being squashed down to about the size of our moon. And that's this new white dwarf that they just recently discovered. If you're not really understanding how dense this is, a single sugar cube of this material would probably weigh as much as every single automobile on planet Earth. That's dense. There's only two other objects in the known universe that are more dense than that. And that's either a neutron star or a black hole. So this white dwarf that they just discovered is pretty close to turning itself into a black hole. And just FYI, you could turn the Earth into a black hole. But you would have to squash the Earth down to about 3 inches. That's the density of a black hole. Does anybody have any questions about anything covered yesterday? Did you have time to look at the handouts? I'm sure if you did, you undoubtedly have some questions.
Yeah, the ultra rays are kind of scary.
The what is?
Ultra rays. I really didn't pay no attention when I'm out there in the sun doing different things. I didn't realize even black people. I'm black, and I think even we need suntan. What do you think?
Oh, yes, you do. Your skin burns just as easily as mine does. The difference is mine burns a little easier, that's all. But yes, yours does burn. Um, and I did mention this yesterday. If you look it up on the internet, there's a really nice product line out there. The clothing is actually UV rated, so it's like wearing sunscreen. It's pretty cool stuff. I bought 2 T-shirts from them just to like wear at the beach or something. So pretty good stuff. Yeah, if we were not protected from all of the ultraviolet that the sun has to put out, life wouldn't exist on Earth. The ultraviolet light that gives you the sunburn at the beach, only a very small amount of all the ultraviolet light that the sun puts out, only a very small amount actually strikes the surface of the earth, yet look what it does to you and me. So can you imagine if we stripped away the magnetic field or the parts of our atmosphere that block ultraviolet light, if we got rid of all those protective devices and all that ultraviolet radiation hit the earth, within a single generation, life wouldn't be here on Earth anymore.
So how's this fit in with the ozone?
Well, the ozone protects us from ultraviolet. It's not perfect at it because some ultraviolet does reach the surface of the earth, and that's how we get sunburns. But you're right, ultraviolet is the magnetic field does most of the work, but the ozone in our atmosphere also contributes to the protection. It's not perfect, however. It does allow a little bit to strike the surface of the earth. And it's the source of cancer for most of us who end up with skin cancer. And every time one of those astronauts goes up into space, there is nothing between them and the sun. So this is part of the reason why when these guys come back from a visit to the space station, they're quarantined not to protect you from any disease they may have brought back. No, what they're doing is they're giving these astronauts extremely thorough physical exams to make sure that they haven't suffered any of the harmful effects of all this radiation that the sun puts out. So every time those astronauts go up into space, they're playing Russian roulette with their health. The other thing that going into space is bad for humans is, as it turns out, everybody, I've mentioned this before, that if we find another planet to live on somewhere, it needs to very closely mimic the conditions here on this planet. Otherwise, we are going to have to adapt to this new environment, whatever this new planet is, and that might possibly mean genetic changes. Well, anyway, here on the Earth, when these guys come back from being in space, they're given these very extensive medical exams to determine whether or not they've got any effects of this radiation. And fortunately, we've not had much of a problem with it so far. But there's another side effect of being in space that you might not think about. You were born and raised on the surface of this planet, and that means that your body has adapted to the pressure conditions here at the surface of the earth and the gravity conditions. You weigh 160 pounds precisely because of the gravity of this earth. If the gravity were any less, you'd probably weigh 130 pounds. Well, anyway, your musculature has adapted to the gravity. The average musculature of a human being is designed to counteract counteract the effects of gravity on this planet. Well, when you go into outer space, there is no gravity. So why do you need muscles? So every time these astronauts go up into space, a serious problem that they all run into is when their muscles begin to atrophy because they don't need them. You've seen pictures of these guys floating through the space stations before. What the heck do you need legs for? You can float everywhere you need to go. Well, the problem comes from the fact that the single most important muscle in your body is your heart. And your heart does not have to work as hard to pump blood through your body because there's no gravity. So therefore, the heart muscle becomes weaker and weaker and weaker the longer you stay in space. So this is why these astronauts go through this extensive medical testing before and after each trip up into the space station. A lot of these astronauts train physically as if they were professional athletes. You know, they run marathons, they enter weightlifting contests. And the reason they do this is that they need to be in peak physical condition when they arrive at the space station in order to withstand all of these negative effects on their body. But if they're in space for more than, say, 6 weeks, say they're up there for 3 or 4 months, it doesn't matter how much training you got down here on the surface of the Earth. You could be a world-class marathon runner. But when you come back to the surface of Earth after 4 months in space, you have to be carried off the space shuttle because you are too weak to walk. And we want to go to Mars. Can you imagine being in a spaceship? Right now, our current technology, the fastest thing we have will get us to Mars somewhere between 6 and 9 months. So let's say, you know, let's look at it on the optimistic side here, and we get there in 6 months. Well, imagine living in your closet for 6 months with no gravity. See, this is a problem. You need the astronauts to be in peak physical conditioning when they arrive at Mars. How are you going to do that? So that's one of the technical challenges. Besides the fact that we need to make faster spaceships, we also need to make safer spaceships. Okay. Let me begin.
Recording in progress.
Okay. I am aware of the fact that you are not able to see me. This has happened to me once before. And as it turned out, I had to completely shut down my computer and turn it back on again for the video to come back. And well, I've chosen not to do that this time because that would probably take me a good solid 10 minutes to complete. And I know you guys don't want to stick around that long. So anyway, we'll continue with the audio only, and hopefully we won't have this problem tomorrow. So far, yesterday, what I covered on the study guide was electromagnetic waves and the spectrum. Now, I know that was a lot of information to give to you, and it sounded complicated at times. Here's what I need you to know and understand for exam 1. First, solar energy is created by fusion. Fusion in the center of our sun. That process that we call fusion is the joining of 2 atoms. The center of our sun is at approximately 18 million degrees, and that's about the temperature you need to be able to slam 2 hydrogen atoms together. I wish I could be in a classroom with you because I could demonstrate to you very easily why you need 18 million degrees. You know, what's with this ridiculous number here? Why does it have to be so hot? Well, there is a reason for that, but it's rather difficult for me to demonstrate to you, especially when we don't have video today. So maybe later, okay? So fusion is going to create solar energy. Fusion is the joining of two atoms. Now, solar energy is that electromagnetic spectrum. The sun creates all of that. It creates radio waves, it creates sound waves, microwaves, X-rays, visible light, ultraviolet. It creates the whole thing. What I need you to know and understand for exam 1 is, or exam 2, is that our magnetic field is responsible for protecting us for the most part. Our atmosphere does not play as big a role in the protection that our magnetic field does. However, it does provide some protection, and Horace brought one of those points up earlier. One of the gas molecules in our atmosphere is called ozone, and it helps protect us from the ultraviolet. Not 100%, but that's what it does. So what you need to know is, everybody, of all that solar energy that the sun manufactures and puts out into space, the only portion that gets through all this protection and actually strikes the surface of the earth is a little bit of the infrared, all of the visible light, and a little bit of the ultraviolet. That's all that gets through, everybody. The other confusing part, which I was anticipating some questions, but I didn't receive any, but I'm anticipating, or I'm guessing some of you are still a little confused as to what's going on here. In the handouts that you have, one of the pages describes to you a relationship between the frequency, the wavelength, and energy. Now, the frequency I spoke about first yesterday. Remember, I described the sound of my voice as being 600 hertz, and then I worked my way up all the way to gamma rays, which were about 10 to the 18th power. We were going up in frequency. That's what we were doing. We were going from sound waves. We went up to microwaves, which is 10 to the 6th power. Microwaves, your cell phone, that operates at a frequencies of 10 to the 9th power, and we just kept going up and up and up, okay? So we went up in frequency. In that relationship, it says the size of the wavelength gets smaller as you increase in frequency. If you remember yesterday, I said everything about solar energy is measured against 1 second of time. 1 second. How many waveforms can you fit into a 1 second time frame? So in the case of the sound of my voice, I said it was 600 hertz. So you're basically looking at squeezing into a 1 second time frame 600 of those individual waveforms. By the time you get up to visible light, everybody, you are now between the frequencies of 10 to the 14th and 10 to the 16th. But you still have to squeeze that into a 1 second time frame. So you can imagine that an individual waveform is incredibly small. So here's the first relationship, everybody. When you go up in frequency, the size of the wavelength gets shorter, much shorter. The third component to that relationship was energy. Once again, we are going up in frequency from the sound of my voice up to gamma rays. As you move in that direction, the wavelength gets shorter and the energy content of the waveform increases. One way to remember that, I brought up a little hint for you. I asked you, what did you think was hotter, red hot or white hot? If you look at the color spectrum, everybody, the color red is near the infrared, and the color white is near ultraviolet. So on the diagram where it says IR, that means infrared, and I said you perceive it as heat, okay? Ultraviolet may not feel hot to you, but it contains more energy. Why don't you feel heat? Because the size of the wavelength of ultraviolet is so small, everybody, that it passes through your skin as if it wasn't even there. It will eventually strike the soft tissue in your body. Hopefully it doesn't destroy cells and create some kind of genetic anomaly, which we call cancer. But nonetheless, that's part of the reason why you do not perceive heat from ultraviolet on the surface of your skin. Oftentimes you don't feel that until the next day when the sunburn kicks in. So as you go up in frequency, you increase the amount of energy in the waveform. Another example that I gave you was your car parked in the parking lot and your windshield is exposed to the sun. Now, visible light is going to pass through that glass windshield like it's not even there. But visible light contains energy, everybody. It's another waveform, just like heat is. The difference is you can actually see visible light. You can't see heat. But as it passed through the windshield of your car, it's also passing through the cloth and the vinyl seats of your car, where it will eventually make contact with the metal springs in your seat. When it hits the metal springs are much more dense than the glass. So they are going to reflect the energy back toward the glass. The difference is, everybody, it's going to strike the metal spring like it was visible light, which means a short wavelength. But when you hit something, think about this, everybody. If you ran a stop sign and T-boned another car, aren't you transferring energy from your moving car onto the car that you just hit? The same thing is going to happen with the wavelength, the visible light. When it strikes the coil in the seat of your car, it's going to lose energy to the coil. And if you look at those relationships I just finished describing to you, as you go up in frequency, I said the size of the wavelength gets shorter. I also said the amount of energy increases. The exact opposite is true. So if you go from a shorter wavelength to a longer wavelength, you have decreased the energy. When that wavelength struck the metal coils in your seat, it gave up some of its energy to the metal coil. It lost energy, which means it became longer. And now it's too big to get out of your car. It can't pass through the glass anymore. So it's trapped inside your car. And when you come out from shopping at the shopping mall and open up your driver door, this blast of hot air comes out at you, doesn't it? So that's solar energy. Now, as it penetrates through the magnetic field and our atmosphere, two things are going to occur, everybody, at least as far as it as it applies to this class, you need to start thinking of Earth's atmosphere as almost like a solid object, even though it's not, it's a gas. My point is, we as humans tend to dismiss the atmosphere because we take it for granted. You can't see it. You can occasionally smell it, but it's not something you can grab hold of and say, here it is. So we tend to dismiss it out of our mind. But what you have to realize is that if you had the ability to actually see the atmosphere, let's suppose you're in a spaceship and you're outside the Earth's atmosphere looking at the Earth. And let's say that you had the ability to actually see the air. The surface of our atmosphere, you're in outer space looking at the Earth. So the very topmost portion of our atmosphere, as it surrounds the Earth, would almost look to you to be the surface of an ocean with waves undulating up and down, except it's not water, it's our atmosphere. And you and me are at the bottom of this atmosphere. That makes us bottom dwellers. When solar energy passes through our atmosphere, it's no different than the solar energy coming into contact with those metal springs in your seat. It's going to give up some of its energy to our atmosphere because it's going to keep our atmosphere in a gaseous form. We as humans like oxygen that is in a gaseous form. You can't breathe solid oxygen. So the sun's energy not only keeps our oceans liquid, everybody, it keeps our atmosphere in a gaseous form. Because without the sun, everybody, our atmosphere would freeze and fall to the ground, just like any other object would. And that's why I'm emphasizing this, because oftentimes we dismiss it because we can't see it and we can't grab a hold of it because it's a gas. But trust me, if you freeze the air, it will turn solid, and then you'll be able to pick it up and hold it. You won't be able to breathe very long, but you'll be able to hold it. So it's going to give up some of its energy to the atmosphere. And because the Earth is receiving a constant stream of solar energy from the sun, as this energy passes through the atmosphere and the solar energy passes on some of that energy to the atmosphere itself contains energy because it's a gas. If you were to heat up a pot of boiling water on the stove to the point where it was turning into vapor, and then you turn the flame off, everybody, the steam that you just created, isn't it going to condense backwards into a liquid? Because you turn the flame off. So if you turn the sun off, everybody, our atmosphere will freeze. So our atmosphere has some of the sun's energy trapped within it. And it is referred to here on this earth as the solar constant. And it is equivalent to 1.92 watts per cubic meter of air. Excuse me, cubic centimeter. I'm sorry, cubic centimeter. If you're not familiar with the metric system, 1 centimeter is a little less than half an inch. 1.2 or 1.92 watts may not sound like a lot of energy to you, but when you multiply it by all those cubic centimeters, everybody, our atmosphere is in possession of an awful lot of energy. To put 1.92 watts in perspective, everybody, the light bulb in your light on your desk in your bedroom is probably a 60 watt light bulb. So our atmosphere contains 1.92 watts per cubic centimeter. It's keeping our air in a gaseous form. Now, that energy is going to continue on its way through the atmosphere where it will eventually strike the surface of the Earth. And based on exam 1 material, everybody, when solar energy strikes the surface of the Earth, what do you suppose it's most likely to hit? Water. Most of the surface of Earth is covered in water. Yes, it's going to hit dry land, but most of the surface of Earth is covered in water. The most intense amounts of solar radiation are going to strike the Earth along the equator, whereupon the water will now absorb most of the rest of the energy that is left over. Because you have to keep our oceans liquid, everybody, and our oceans only stay liquid because they have solar energy trapped in it to keep it liquid. If you turn the sun off, everybody, our oceans freeze right along with the atmosphere and you and me and everybody else on the planet. Okay? So you've got this remarkable situation here where you have solar energy created in the interior of the sun. It's radiated out into space where fortunately most of it is blocked from entering through to the Earth's surface. But what does enter Earth and strike the surface of the Earth, it's going to hit water. It's going to keep that water liquid, and ocean currents are going to circulate that solar energy around the planet, whereupon it will then give up the solar energy through our polar regions. So to use a human physiology anatomy, what is the warmest spot on your body? It's typically your core, your torso, your trunk, whatever you want to call it. That's where most of the heat is. Where do we as humans lose most of our body heat? And it's in our extremities. We lose it in our hands and our feet and our head. Well, the Earth functions in a very similar fashion. It's hottest at its core, which in this case is the equator. And it's going to lose its heat out its head and its feet, except we call it the North Pole and the South Pole. That's all. So the ocean circulation, in a way, is kind of like a metaphor for your blood circulation through your body. Okay. So that is section 1 of the material on this outline of the study guide. Before I move over to temperature and calories, does anybody have a question? Everybody understand so far everything I've explained? Anybody want me to repeat anything? Okay. Temperatures and calories, everybody. Once again, this is not a difficult concept. Most of you I know are capable of understanding it. The issue is that this is just new material to you. That's all, okay? So I want to start off with some definitions, because I'm pretty sure there's a misconception amongst many of you that believe temperature is a measure of heat, and it's not. Temperature does not measure heat. Temperature, and this is a definition, everybody, temperature is a measure of molecular motion. That is temperature. Calories. This is the true measure of heat energy. A single calorie, everybody, is the amount, and this is the definition, it's the amount of energy required to raise the temperature of 1 gram of water 1 degree Celsius. A calorie is the amount of energy required to raise the temperature of 1 gram of water 1 degree Celsius. 1 gram of water, everybody, is about a quarter of a whiskey shot glass. It's not a lot of water, but that's basically what a calorie is. It's the true measure of energy. If you ever are outside of your house when the PG&E technician comes by to check your meter, you should take a look at the meter on the side of your house, everybody. It's measuring energy and how much calories you use. So when you get your PG&E bill in the mail, they typically itemize your bill for you. And your energy usage is listed as kilocalories. That's how much energy you used on that particular month. It's measured in calories. Now, temperature is a measure of molecular motion, and what in the heck does that mean? First off, this is a concept that was first discovered and explained, believe it or not, by Albert Einstein. He's the one who proved, in addition to all the other things that you are familiar with, E equals MC squared and all that neat stuff, he's also the man responsible for proving that atoms actually existed. You see, in the year 1900, we were not certain that atoms actually existed because we did not have the technology to explore objects that small. So Einstein was able to prove it mathematically. And he started off by explaining a simple concept that if you as a student, if you've ever taken either a biology lab class or a chemistry lab class, you're familiar with looking through a microscope and seeing something that's called Brownian motion. When you look through, if you have a little petri dish with water, and if you throw some small grass seeds onto the surface of that little bit of water, and then you look at the grass seed underneath a microscope, you would think that the grass seed should just sit there and float about. But when you look at it under a microscope, it appears to jiggle. And that's called Brownian motion. And nobody understood what was happening until Einstein came along. And what he proved mathematically was he had just finished proving the existence of atoms. A single atom is too small to push around a grass seed. By comparison, the grass seed is the size of an elephant compared to an atom. So one single atom is not going to do it. However, that petri dish with the water in it contains trillions and trillions of atoms. And so what you're looking at, and this is what Einstein proved, is the constant bombardment on one side of the grass seed by a bunch of atoms, and then another bunch of atoms are going to hit the grass seed from the opposite side, and it's going to give the grass seed the appearance of a jiggle. It's going to move. And in the case of temperature, everybody, when we measure temperature, what we're measuring is molecular motion. How many molecules in your mouth are colliding with the thermometer that we just shoved under your tongue? It's not actually measuring heat. Now, why would it measure molecular motion and not raw heat? Well, Do you remember my explanation of fusion, that it took 18 million degrees to get two hydrogen atoms to fuse? What that means is, everybody, at 18 million degrees, the hydrogen atoms are moving around pretty damn fast. And if they should happen to collide with each other, they're going to fuse. Now, the atoms that make up your body are not moving near as fast. But when you run a temperature, everybody, not only do you get physically hot, but your body's not creating heat in the traditional sense of the word. The heat that you're feeling and the heat that we call your temperature is actually your metabolism kicking into high gear because it's trying to fight some kind of infection. And so the molecules in your body are moving much, much faster. And we record this by taking your temperature. And so when we see a number that is higher than normal, we go, oh, okay, his body is trying to fight an infection. When it comes to calories, I said that it was the amount of energy necessary to raise the temperature of 1 gram of water, 1 degree Celsius. I want to make a comparison once again to human physiology that most of you can relate to. You have approximately 10 pints of blood in your body. At any given moment in time, about 2 pints of that blood is tied up in your major organs, which means that the remaining 8 pints of blood is actually circulating through your vasculature throughout your body. Now, you've been told as students, and maybe you've heard this on documentaries and TV, we humans are made up mostly of water. And that's true, we are. Of those 8 pints of blood circulating through your vasculature, approximately 5 pints of that is water. The rest of it is chemicals. So you have 5 pints of water flowing through your vasculature. A single pint is 16 ounces. A single ounce is equal to 28 grams. For all you pot smokers in the room, you're familiar with that number. There's 28 grams in a single ounce. And it's going to take the amount of energy required to raise the temperature of 1 gram of that water, 1 degree Celsius. So there's 28 grams in an ounce. There's 16 ounces in a pint. So 28 times 16 is 454. But you now have 5 pints of that water floating through your bloodstream. So 5 times 454 is approximately 2,200. What is your daily recommended caloric intake? 2,000 calories. Why? Because you need to maintain the oven, so to say. I'm speaking metaphorically here, but you need to stoke the oven to keep your body running. It's energy, everybody. And so you need to input 2,000 calories a day. Keeps your metabolism going, keeps all those electrolytes pumping through your body, which in turn causes your organs to function. So that's temperature and calories. There's going to be 3 temperature scales that I'm going to bring up in the class. However, on exam number 2, the scale I'm going to ask you to be familiar with is Celsius, not Fahrenheit, Celsius. I'm not really sure why the United States has not embraced the metric system yet. We're one of the very few industrialized nations that still uses the standardized unit of measurement. Even Mexico uses the metric system now, and so does Canada. We still use inches and feet. Everybody else uses millimeters, meters, kilometers, and so on and so forth. And my rationale for the metric system is real easy, everybody. First off, in the Fahrenheit system, most of you, I think, are familiar with the fact that water freezes at 0 degrees, or excuse me, 32 degrees Fahrenheit. Water freezes at 32 degrees Fahrenheit. Water turns to a gas at 212 degrees Fahrenheit. Who the heck came up with these numbers? Well, I was talking to a chemist on the staff a number of years ago about that, and he tells me that there was an Englishman in the 19th century, this is the early 1800s, and his name is Fahrenheit. And he's the one who developed this system of water freezing at 32 degrees and vaporizing at 212 degrees. Your body temperature in the Fahrenheit system is 98.6. You've heard that all before. Here's my sales pitch for the metric system, everybody. You know what temperature water freezes at in the metric system? 0. You know what temperature water vaporizes at in the Celsius system? 100. You tell me which one's easier. For those of you in this room who are mechanics and used to working with tools, imagine this, if you will. You've just purchased yourself some old classic muscle car and you're trying to restore it. So you are going to replace some parts. So you're going to crawl underneath that muscle car that you just bought. And you've got a wrench in your hand because you're going to change some parts out in it. And when you put the wrench on the nut, you find out that the wrench is just a little too small. You need one a little bit bigger. Well, if you happen to have a 7/16 inch wrench in your hand, what's the next size up? Real quick, come on, somebody tell me. Think about it. Here's my sales pitch for the metric system, everybody. If you're working on that same car and it's built entirely out of metric parts and you crawl underneath that car to undo a bolt and you've got a wrench in your hand that is slightly too small, in the metric system, it would be, say, for instance, 10 millimeters. What's the next size up? 11 millimeters. Then 12, then 13, then 14. How hard was that? In the way we measure things now, if you have a 7/16 inch wrench in your hand, what's the next size up, everybody? Unless you're familiar with it, you don't know because it's 1/2 inch. Plus, your body temperature in Celsius system is 37 degrees, period. That's it. I'm not going to ask you to do any math conversions from Fahrenheit to Celsius on the test, but what you do need to know is water freezes at 0 degrees Celsius, water vaporizes at 100 degrees Celsius. Now, I'm going to be sending you some handouts that have temperature scales on it, and it's going to show you the 3 different temperature scales: Fahrenheit, Celsius. The third one is called the Kelvin system. Now, I just got through telling you temperature is a measure of molecular motion, okay? The more, if you've got an object, the more the molecules in that object are moving, the hotter it gets. Because the moving molecules represent energy. The Kelvin system of the 3 temperature scales, everybody, is the most accurate at describing molecular motion. The only thing about the Kelvin system I want you to know for exam 2 is 0 kelvins. 0 kelvins. Notice that I did not say 0 degrees Kelvin. For those of you who are going to end up in a chemistry class at some point, it's just 0 kelvins, not 0 degrees Kelvin. 0 kelvins is absolute zero. And what that means is, everybody, absolutely no molecular motion. You've seen in movies before where somebody has a container of liquid nitrogen and they stick a rose in it and the rose comes out rock solid. Matter of fact, it's so hard, it's brittle. Do you ever see that, where the guy takes the rose, he dips it in the liquid nitrogen, freezes the rose, and then he taps it on the table and the rose shatters like a piece of glass? The liquid nitrogen was not at absolute zero, but it was close. Absolute zero on the Fahrenheit scale, everybody, is minus 456 degrees or 459 degrees. That's absolute zero in the Fahrenheit scale. So that's pretty cold. And at that temperature, there is no colder temperature, because there is absolutely no energy in the object that you are trying to measure. If the temperature of that object is 0 kelvins or minus 459 degrees Fahrenheit, the molecules that make up that object are completely stationary. They're not moving. And when you inject energy into something, you're merely speeding up the molecules that make it up, and you are spreading them out further and further apart. So think of it this way: when you apply energy to a solid object, what makes it go from a solid to a liquid? Yes, you are inputting energy into it, you're making it hotter, but what exactly is happening at the molecular level when you do that? When you take a solid block of ice and you put energy into it and you melt it and you turn it into liquid water, that energy is trapped in the water now. It's keeping the water liquid. And exactly how is it doing that? The energy that you put into that water is physically holding the molecules of water apart from one another. And the further apart you are able to push these molecules, the water then eventually turns to a gas. And then you get to the point where you're pushing the molecules so far apart from each other, you can't even see the water anymore because the molecules are so far apart from each other. This is why you can't see our atmosphere, because oxygen is a solid at about minus 300 degrees Fahrenheit. Oxygen turns into a gas at about minus 250 degrees Fahrenheit. It has different temperature properties than water does. So don't think that just because water freezes at 0 degrees Celsius that everything else does too. No, that's not true. If you are an oxygen molecule living on planet Earth, the average temperature of the surface of Earth is approximately 56 degrees Fahrenheit. That's the average when you average out the polar regions with the equator. It's about 56 degrees. If you're an oxygen molecule, everybody, that's like living in hell itself, because after all, you vaporized at minus 250. Now it's plus 56 degrees. From your perspective, that's a 300-degree temperature increase. It's hot as hell here if you're an oxygen molecule. So that's what putting energy into an object does. It speeds up the individual molecules and it pushes them apart. And that's what causes the transition between being a solid, liquid, and a gas. The molecules in a gas are so far apart from each other, you typically can't see the gas. So you can't see the oxygen in our atmosphere. And that's what I meant earlier about if you were somehow to remove all the energy from our atmosphere, it would be no different than any other object. It would turn to a solid and it would fall to the ground. Okay. Are there any questions? I'm finished for today. I will be sending you a diagram on temperatures and calories. Okay. And hopefully tomorrow I will get the video fixed on this Zoom meeting. Okay.
Recording stopped.
Are we able to get the recording today?
Yeah, you will. It'll just be my voice though. You won't be able to see me.
Okay, I understand.
Yeah. So this has happened to me before. It's not, I mean, I've got all my controls right here in front of me and I've got the one that says, you know, start the video, but obviously it's not working. So what it took for me to fix it in the past was to completely shut down the computer and turn it back on again. Oh, wait, look, video just came on. Wow.
Okay, let's start all over. Okay, so that's what I do to make my notes. I record, I would listen to you and then I go ahead and listen
Take notes off the recording.
take notes because
You can stop it.
well, I don't write that fast and I'm my age right now, my eyes don't see good. But also the math part, I do have some questions for you next time around. I'm trying to really understand the math on all of this. And it seems like it's more than just multiplication and division. And
Well, it really is, Horace. It's just you're not used to this. That's all. Like you said, you know, you've been out of the game for a while. But in actuality, the math that's being shown on those handouts is probably 6th or 7th grade math.
oh no, I gotta get my grandkids.
It's just that you've been away from it for so long, Horace. So don't feel bad.
But you're talking about 10 to the 16th power and all that stuff. And I'm thinking, what?
Yeah, it's 10 with 16 zeros after it. That's a big number. Okay. The other thing I wrote on those diagrams too, when you look at the number lines, Horace, you know, look at the number line that has 10 to the 3rd, 10 to the 6th, 10 to the 9th on it.
I
And
saw
notice,
that.
yeah, notice that underneath it, I wrote the mathematical term for it. So 10 to the 3rd is referred to as kilo. 10 to the 6th is referred to as mega. 10 to the 9th is giga. And 10 to the 12th is tera. And 10 to the 15th is exa. If you use the word mega, let's say you listen to FM radio and you listen to B95, they're transmitting their frequency is 95,700,000 hertz. That's 95.7 or 95.7 megahertz.
Oh, okay, I get it. But I'm gonna wait for your recording and I'll start taking
Okay.
notes.
Just trying to make the diagrams a little easier to understand. If you attempt to do the math, Horace, what you are doing is converting a frequency to a wavelength. That's what you're doing, or converting a wavelength back to a frequency. So that's the purpose of the math. If you actually wanted to do it, please notice in my explanations on the handouts that 3 times 10 to the 8th is always in the numerator. It's always on the top portion of the division.
Okay.
Because that's the speed of light. 3 times 10 to the 8 meters per second. That's the speed of light. So if you want to take a wavelength and convert it back into a frequency, you take 3 times 10 to the 8th and divide it by the wavelength, and the answer will be the frequency. And if you
Okay, I get it.
Yeah. And then if you want to take a frequency and convert it to a wavelength, you take 3 times 10 to the 8th, divide it by the frequency, the answer will be a wavelength. Okay. And I won't bore you with all the details yet. I'll probably do that tomorrow, but I'll explain to you exactly how to do the division, because there is a trick to it that, once again, Horace, don't feel bad. You've just been out of the game for a while. That's all. It doesn't mean you can't understand it.
Well, I'm trying.
No, I know you are. It's just keep in mind you haven't been there for a while. That's all. So you're getting back on that bicycle. That's the way to look at it.
Yep.
Mm-hmm. Does anybody else have any questions, any comments, anything like that? You see all the information that we're learning about how our atmosphere works and our relationship to the sun. It's also helping us understand what's going on other planets, because physics is physics no matter where you go in the universe, everybody. You know, I know it's kind of fun to watch science fiction movies, and, you know, at some part of the universe, they're able to do, you know, all kinds of magic, way cool things. And, you know, the realist part of me, I can watch a science fiction movie and completely enjoy it and have a good time at it, not stress over it, because it's just a movie after all. But in reality, the science that they display in these movies is totally bogus. Physics is physics. It doesn't change whether you're here on the Earth or on some far distant planet on the other side of the galaxy. You know, what goes up has to come down no matter what planet you're on. And so my favorite science fiction fallacy that I point out to, you know, people that are diehard science fiction fans is when human beings travel faster than light in order to be able to go to all these other places in the universe. Well, we as humans, there's a technical difficulty that we have not solved, and I don't believe science is going to solve this problem for a very, very long time. And that's called inertia. Have you ever sat in your car in the front seat, you're sitting in the passenger seat, and the driver suddenly hits the gas real fast? All of a sudden, doesn't that throw you backwards into the seat? When the car moves forward, you get pushed backwards. That's inertia. And that was from a moving automobile. You were at a red light and then suddenly it turned green and the driver just hit the gas real fast. And you went from 0 to 60 in like 3 or 4 seconds. So you got pushed backwards into the seat for just a few seconds. Now, imagine you're on Starship Enterprise and you are Captain Picard and you say, give me warp 2. And you tell Mr. Data, engage. You're going from 0 to multiple times the speed of light. Captain Picard would have been thrown through the back wall and out the backside of the spaceship when it took off in one direction, and his body was thrown out the wall at the backside of the ship, because we haven't solved inertia yet. But it's a movie. Just enjoy it. I grew up in an era when science fiction movies were pretty cheesy. They didn't have modern day CGI. And so spaceships were held up by strings and that kind of thing. And in the really bad movies, you could almost see the string hanging from the top of the picture frame, holding up the spaceship. But whenever the movie involved outer space, the one thing that you notice in these movies that's different from movies today is that they never try to explain the technology. You watch a 1950 sci-fi movie and they've got rocket ships that go to Mars. They don't explain to you exactly what that rocket ship is or how they came about inventing it. They have it, and it moves really fast and it takes us to Mars in a matter of days instead of months. You see, today's science fiction movies, they try to make an attempt to explain to you what the technology is in order to give the movie an air of legitimacy, to make it believable. So, you know, they throw all that techno talk into the sci-fi movies. They never used to do that in the 50s and 60s. You just had to believe they had the ability to do whatever it is they were doing. So physics is physics. Doesn't make any difference what part of the universe you're in, whether you live on Tatooine, or if you're fighting the evil empire, or if you're fighting Klingons. You have to obey the laws of physics, and one of them is inertia, and we haven't solved that one yet. Are you familiar with the fact that fighter pilots in jets have to take special training in inertia before they're certified to fly? Because they're flying these super sophisticated, ultra fast jets. Now, these jets are capable of moving at over 1,000 miles an hour. Can you imagine what happens to your body when you have to make a hard right-hand turn at that speed? These fighter pilots have to be in peak physical shape in order to tolerate that kind of abuse that their body goes through. And we have not figured out a way to put a pilot in a seat and make him go really fast and then not feel the effects of that speed. We have not figured that out yet. And I don't think it's going to be hundreds of years before we do, because it's going to take some magic Star Trek technology in order to solve that problem. And that's why traveling in space is so full of obstacles and hurdles that we as a species have to overcome. We have to make it safe for humans in many different ways. And I've already explained a couple of them to you. The effects of gravity, the effects of time, because we can't move that fast. It takes us forever to get any place in the solar system. I mean, it takes 9 months to get to Mars. Can you imagine being stuck in your closet for 9 months? And then when you get to Mars, you better be healthy when you get there. You know, you can't be sick when you get to Mars. And then you got to come back home. You got to spend another 9 months in a closet before you land on Earth. So whoever the first people that land on Mars are going to be some pretty extraordinary individuals. They're going to be not just very intelligent people. They're going to be in world-class athletic shape. So these are going to be some rather unique people that make that first trip to Mars. And the reason I'm bringing that up, everybody, is because according to a lot of the science journals, we're hoping to put a human being on Mars sometime in the 2030s. The newest generation of rockets is supposed to be way faster than what we currently have. The fastest rocket we have in our inventory right now will push a space capsule at about 25 to 30,000 miles an hour. And on a galactic scale, everybody, that's like driving in the right-hand lane at 35 miles an hour. In order to get to Mars in a reasonable amount of time, you need to do, probably 150,000 miles an hour. And that would get you to Mars probably in about 2 to 3 months.
Why are they so obsessed with speed? Star Trek was obsessed with pulling the molecules apart and transporting them someplace and then putting them back together again.
That's another technology that I don't think humans are ever going to see in reality, because, and I'm going off track here, but when Mr. Einstein came up with all his famous formulas in the early 1900s, and the most famous one being E equals MC squared, what most of you may not be familiar with, everybody, is he's also the inventor of quantum mechanics. And this goes to your statement, Horace. Einstein's theories work really well at describing what we see in the universe. Okay, his math formulas, they've given us all kinds of insights as to how stars work, how planets move, how galaxies merge with one another. His math that he invented allows us to calculate what is going to happen in the future. And what I mean by that is when two galaxies collide with each other, we know what the outcome is going to be, thanks to Mr. Einstein. However, his formulas do not work with objects smaller than atoms. And this is where quantum mechanics comes in. And the difference between the very small world and the very big world, in the very big world, his formulas work just fine. But in quantum mechanics, the math that is used is basically a very sophisticated form of statistics. And if you've ever worked in math before, statistics is not a definite, it's an average. You're calculating an average of something. Whereas in regular math, you're coming up with a definite answer. It's black or white. There's no in between. But in quantum mechanics, there's all kinds of in betweens. And that drove Einstein nuts. He didn't agree, even though he invented it. He refused to believe it because they couldn't predict how atoms would behave. Because they were thinking of atoms in terms of atoms being, like any other solid object. You can predict, if you roll it down a slope, you can predict how far it's going to roll based on how big and heavy it is. But what they're discovering is in the quantum world, measuring that kind of movement is near impossible. You can calculate its direction of movement, but you can't calculate the exact time in which it will finish. Or you can calculate its exact time to finish, but you can't calculate its direction. See what I mean? And Einstein was like, this is nuts. You can't do this. But yet there it is. And so the end result of it is, and this goes to the transporter you're talking about, is you want to take a human body and take all of the molecules in your body, turn it into an energy data stream, and then reassemble them at the other end. In this case, it's from the ship to the planet's surface. Well, when you rematerialize that person, the molecules in their body have to be in the exact same position they were in the instant before you turned them into energy. We do not have the computing power to be able to calculate where every single molecule in your body is physically located at any given moment in time. How many molecules do you suppose make up your body? Trillions. And you have to do the math and calculate each and every one of those molecules that make you up. You have to calculate not only its precise location, but you have to also include what direction is it moving in. And then all of that information has to be transported to the other end and your body reassembled. Do you see how complicated this is? So inventing transporter technologies, even 500 years from now, I don't think is going to be a reality. We just don't have the ability to do that. But there's a lot of other cool things on the horizon, though, but that's not one of them, unfortunately. So Captain Picard is going to have to get into a shuttle and manually drive down to the planet. I grew up a Trekkie fan, so I know what you're talking about, Horace. My younger brother was he worked in law enforcement his entire career, and I could never watch a movie with him because he was the guy that talked through the movies. Oh, the police don't really do that. They don't really shoot guns like that. Bullets don't really behave like that. And I constantly had to keep telling him, it's a movie. Just enjoy the movie. Don't worry about how they do it. And I promised him I wouldn't talk through science fiction movies. Okay. Any other questions? No? All right. I'll see you guys tomorrow.